So today we're very privileged to have Nuh Gedik from MIT. One of the exciting drives in condensed matter physics these days is ongoing progress in what we can do with light, and in particular with ultra-fast light. And the Gedik group is really at the forefront of this. I won't try to say anything more than that because, because we'll only get me in trouble, but I'm looking forward very much to this.
All right, so I first would like to thank you for the invitation to NYU. This is my first time in NYU, and I'm really enjoying my visit. So what I would like to do today, I want to tell you about some of our recent experiments in topological insulators. And what this picture is supposed to illustrate is that in a topological insulator, electron spin direction is locked perpendicular to the direction of motion. So you can see electrons going one way have one spin, and going the other way have the other spin. And one thing, for example, that we can do with light, by using the helicity of the light, we can couple to different species differently. Okay, so this is what I'm going to be telling you about. First, because this is still a new topic even in condensed matter physics, I want to tell you what are topological insulators. And then I will tell you how we can both probe and control properties of these materials with light. And at the end, if I have time, I'll tell you what's happening in our lab, or what will happen in our lab later on. Okay, so what is a topological insulator? So in condensed matter physics, the way we usually classify different phases of matter is by talking about what symmetries do they break. And this paradigm is due to Landau. For example, you can think about liquid crystals where translation symmetry is broken. You can think about magnets where rotational symmetry is broken. In a superconductor, it's a bit more abstract. It's the gauge symmetry is broken. But the point is that there is always a symmetry that's broken with a phase. So then, if that's the case, you can define an order parameter, you can do diffraction, etc., etc. Now, it turns out that topological insulators do not fit into this paradigm. So you really cannot really talk about in the same paradigm. So how do we understand then this kind of phase? So it turns out you really have to think about a different way of classifying phases. So to introduce that, I want to walk you through different kinds of insulators you can have. So let's think about the simplest possible one, right? You can take argon, you can cool it down, you will get solid argon, and this is going to be an insulator because electrons are localized around every atom. They're not talking to each other. And also, there's an energy gap. This is pretty much the energy gap between the atomic levels. If you think about more familiar type of insulator, take silicon, for example, in which now atoms are making covalent bands. And instead of just atomic states, you have atomic bands. And then there are still energy gaps between the filled levels and empty levels. And this is as well an insulator with an energy gap of about on the order of 1 eV. Okay, so now the first topological phase of matter is not a topological insulator. It was actually an old state by now. It's the quantum Hall insulator. So this is yet a different kind of insulator that I would like to introduce you. It's important because this is the first topological phase of matter. So what is the quantum Hall insulator? So let's remember the quantum Hall effect. You take a two-dimensional electron gas, you put an external magnetic field, and then you measure its transport properties. You measure the resistance, the usual resistance, and you measure the Hall resistance. You run a current through here, and you measure the voltage, and you divide them, you get the Hall resistance. So when you do this experiment, you see something very, very interesting. So number one is, what do you expect? So when you put a magnetic field, electrons in the bulk of this two-dimensional material, they go through these cyclotron orbits. So you can imagine they're sort of kind of localized. And there will be lambda levels, if you remember, and then there will be a gap between the filled lambda levels and empty lambda levels. If you do the transport, if you now measure these quantities, this is what you see. So this is very unexpected because if you look at the longitudinal resistance, that's this green curve right here, you actually see that as a function of magnetic field, there are some regions of magnetic field the resistance is absolutely zero. So I call this a quantum Hall insulator, and I'm talking about zero resistance state, which is kind of ironic. Now, even more interesting perhaps, if you look at the transverse Hall resistance, that's this red curve right here, you'll see that there are some regions where this thing is constant. It looks like steps or plateaus. Now, if you calculate conductivity, the Hall conductivity, which is 1 over this quantity, it turns out that this thing is quantized. So it is an integer times e squared over h. So all of this weird phenomena really were begging some explanation. It must have been very unusual. And it was indeed, and that's what led to the Nobel Prize in 1980. And the understanding of this effect really comes when you think about what's happening at the boundary of the sample. So what really happens is this. Electrons at the boundary at the edge of this sample, they can't really complete a full circle. So what they really do, they go through these skipping orbits like this, like half a circle if you wish. You can imagine this is going all around the sample, and the direction of the state is really set by the direction of the magnetic field. If you were to reverse it, it would reverse. Now, this is in real space. If I were to represent this in the momentum space in terms of energy versus momentum, you have the lambda levels, you have the gap that I talked about, and you have this one-dimensional conduction state that only goes in one direction, right? The direction is set by the field. Now, one important thing to note here is that if the electrons would encounter an impurity, right, in a regular metal, they will just scatter back. But here, they don't really have the option of going back because there is no state going back. The only thing that they can really do is they need to go around this impurity and keep going. So they really cannot make any U-turns, okay? And this was the reason why the longitudinal resistance goes exactly to 0, because you are turning off these backscattering channels. Okay, so you might say, what does this thing have anything to do with topology? So after all, it's just a name, right? And in this case, this term is borrowed from math, where, when we classify shapes according to their topology, this is a mathematical term. What we are really doing is, you can actually define an integral. This is the integral of local curvature. If you integrate this curvature around the entire surface, it turns out that you get 4 pi times an integer. And that integer counts how many holes is going through your object. For example, a coffee cup has 1 hole going through it, same as a donut. So these actually have the same topological class. If you calculate this integral, it exactly turns out to be the same. Now, similarly, physicists, they can define a quantity similar to the local curvature. It's some other curvature that I'm not going to go into details. It's a property of electronic wave functions. And if you integrate this over the entire Brillouin zone, it turns out that just like this thing is quantized, this thing is also quantized, and that integer that you get when you do this integral is actually the same integer that appears in the Hall effect. So just like these states are the same states, if you can kind of tune, slightly deform the shape, and you're not going to change the topological nature. Just like that, if you do introduce some impurities at the edges, or if you put some imperfections, you really don't change the topological class of this material. That's why this edge state is so robust. It has to be there because this is dictated by this integer. Okay. Now, obviously, just like a sphere is not equivalent to a donut. If you do something violent to this, if you, for example, bring these two edge states together or something, you can now change the topological class of this material. So this is, how much I really would like to spend on this. After all, it's just a name, but it has its connection, from this math, the area of this math. So now, after people figured out this very interesting quantum Hall physics, this was in 1980, then theorists have been thinking about for the past, starting from like past 10 years, could we have this effect at room temperature without the external magnetic field? Because one thing that I glossed over, this quantum Hall physics really is observable mostly when you have the external magnetic field is about 20, 30 Tesla and at millikelvin temperatures. There are some few exceptions, but it's mostly the case. So the question is, can you have this at room temperature with no external magnetic field? So you need to have a way of kind of replacing this external magnetic field with something. And then one idea was that maybe you can replace it by spin-orbit coupling. In what sense? Well, remember the spin-orbit coupling. If an electron, in the classical sense, going around the nucleus, in the rest frame of the electron, this electric field due to the nucleus is really felt like a magnetic field. And the direction of that magnetic field depends on the spin. For spin up, it's one direction. For spin down, it's the other direction, right? So the idea was, maybe we can replace this external magnetic field with this effective magnetic field due to the spin-orbit coupling. So if you want to have a big magnetic field, you have to have a big electric field. That means you need a nucleus with a lot of charge. That's why you really need to look down in periodic table to have high Z materials. So this idea was proposed, and in this case, obviously, two spins would actually, they would effectively feel different magnetic fields because this sign is different for spins, and instead of just getting one state at the edge of the sample, you actually expect two states. So the first theoretical proposal was in 2006, and it was a year later experimentally confirmed in mercury telluride, cadmium telluride quantum wells that indeed what happens is that in the absence of magnetic field, you get quantum Hall-like physics. And with one difference, now you have actually two states. One is for spin up going to the right, one is for spin down going to the left. Now, if you were to represent this in momentum space, now you have to put two lines like this. One is going to the right, one is going to the left, and they are spin polarized. So each spin has a direction. So now the interesting thing is there are still no U-turns because if you want to turn this guy back, you have to flip its spin. So as long as you have non-magnetic impurities, as long as you have time reversal symmetry that's there, then it's still, you really still cannot make any U-turn. So this is still a two-dimensional material, and we are talking about 1D edge state. So this is another term for this. This is a two-dimensional topological insulator. Now, you can generalize this thing into... Can you yes, please.
Go back and say
yes.
Insulator?
It's an insulator because, the bulk of the material, it's not conducting. Yes, it's an insulator. Right, indeed.
And that's because of there was a gap to start with?
There was a gap to start with, yes, indeed, yes. And then if you tune this into the topological regime, which I'm not going to go into details, now you get these conduction channels at the edge of the material.
So you still have conduction at the edges, except that they cancel out.
Say it again, please.
You're saying you have conduction at the edges,
right?
But they're going in two different directions.
That's right. There's a net spin current, but no net electrical current.
And here the magnetic field is really provided by the solid for spinning.
Exactly. Yes. Good. So now you can generalize this into 3D. In the following manner, we were talking about 1D states as a boundary of the 2D system. Now you can think about a macroscopic crystal. And in this case, similarly, because of similar effects, what you're going to have is an electron going to the right will have a spin perpendicularly locked to its momentum, just like this guy, let's say. And the electron that's going in the opposite direction have exactly the opposite spin. But this is true for any direction. So, and the boundary of a 3D crystal is a 2D state. And if you want to represent this in the momentum space, here it turns out that the dispersion for these guys is linear. You can think about like, here you just have one, but if you have a 3D system, you have the entire cone. And the spins are perpendicular to the momentum. They are winding around the Fermi contour like this. Now, you still cannot make an 180-degree backscattering, so this U-turn, a complete U-turn is still prohibited even in these systems. This is how the bulk is going to look like. Bulk will have an energy gap. It will be insulating. But at the surface of this material, you have this conducting state with this weird property that the spin is locked perpendicular to the material. So it turns out that this effect was observed. And these are some of the exemplary materials. Some of the most studied topological insulators are bismuth selenide and bismuth telluride. Most of my talk is going to be about bismuth selenide. So let me summarize the key properties of these materials then. So number one is this spin momentum locking, the fact that the electron spin is perpendicular to the electron momentum. In regular metals or other materials, this direction is arbitrary. The spin direction is not related to the momentum direction. And that has interesting consequences. If you run a current through this material, for example, then you would generate an imbalance between the two spins, and then that will actually lead to a perpendicular magnetization. Now, because of the spin momentum locking, you also will get, absence of backscattering, because you cannot take this guy and put it here. Their spins do not match, and that's why people expect these things to have high mobilities. Now, there's one other thing that we should mention is that
this is all you're talking about
surface. That's right, indeed.
Only
yes.
conduction or surface mobility.
Exactly. That's right.
Because in the bulk, it's
as I will describe, there are some limitations to this. Yes. In the ideal case, bulk should be insulating, but it's not. Right. Okay. So the other thing that we should mention is that this crossing point here, right here, this point is actually very special. This is called the Dirac point, and that point is protected by time reversal symmetry. So as long as you have no non-magnetic impurities, then this actually stays. It's very hard to get rid of this. You cannot really gap out these states. Now, there are other materials which have surface states. There's nothing unusual about having a surface state, but usually if you put a little bit of junk in there, you gap out the surface states. But here you cannot. Okay, so a number of interesting applications, both from the academic sides and also the application side, have been proposed. For example, if you interface the topological insulator with an S-wave superconductor, it was proposed that this interface actually would host novel excitations called Majorana fermions, which are excitations that are their own antiparticle. They can do, they are predicted to be very useful in quantum computation type of applications. There was another interesting proposal, which is that if you were to bring an electrical charge near the surface of a topological insulator, the image charge that's formed inside the topological insulator actually has a field distribution that's identical to a magnetic monopole. That comes about because there's a funny E dot B term at the surface of a topological insulator that modifies the Maxwell's equations. Now, there's a number of other things. People were thinking about doing something with spins, like making spin valves, doing something with spintronics, gating the two sides of a TI differently. You can have condensations, etc. But the point that I'm trying to make is that there is a lot of interest from both sides. Okay, so far I just painted you an idealized picture and what's good about these materials. Let's now talk about some of the challenges that actually motivated my work, and what were some of the problems that we didn't know about. So as it was raised, everything that I was telling you about was the property of the surface. But it turns out when you make these materials, it's very hard to make them insulating. Just because when you grow bismuth selenide, for example, there appears to be some selenium vacancies that you can never get rid of, which dopes the sample. When the sample is doped, the material is not insulating, but it's essentially a metal. There are a lot of bulk carriers around as well. If you were to do a transport experiment, for example, it's very hard to separate surface from bulk. Now, the other thing that that was very interesting is this spin momentum locking is the basis of many of the proposed applications, and it wasn't clear how this would hold in real materials when you actually go into high energies when this material is doped. How is the spin momentum locking going to hold? Is it going to be in the ideal case? And the other thing was about dynamical properties of these materials. What would really happen when you shine light onto them or pass a current through them? How would their properties change? So to study these materials, now in the early days, they were mostly studied by two surface-sensitive techniques. So angle result photoemission spectroscopy, I will go into details of this technique, so-called ARPES, is a technique where you shine light, you kick an electron, and you measure a band structure by measuring energy and momentum of the electrons, or scanning tunneling microscopy, where you bring a tip and you scan the surface, and you actually can get a local density of state. So those were, perhaps rightly chosen because they are very surface-sensitive. You're trying to study the surface state. Now, I come from the background of optical techniques, so my expertise was using light to study different materials, and I wanted to use this for the following reasons, because with light you can do a lot more. You can get spectroscopic information. You can also, if you use pulses of light, you can do time result studies. If you use the helicity of light, you can even, in some systems, couple to the spin. So that's what we've been doing at MIT, having fun a lot with these techniques. What I will tell you today is just one of our works in which we used ultra-fast optics. We coupled it with ARPES, and we were able to do time result measurements of the electron band structure, and we can do some control. So let me begin first by introducing you to the technique. So before that, here are the real people who did the work. My first graduate student, Yuha Wang, he now moved on. He's actually a professor in Fudan University now. My graduate student, Fahad Mahmoud, is the person who took over from Yuha. My colleagues at MIT provided me the samples, and these are the agencies that gave us money to do this work, and we benefited greatly from discussions with our theory colleagues. So what is ARPES? ARPES is a technique where you actually shine light, and you kick out an electron, and by measuring energy and momentum of the electron, and knowing what the input energy of the light, you can back out what must be the energy and momentum of the electron inside the solid. Now, this technique has made tremendous contributions to condensed matter physics in the past 30 years. And the way you do these experiments, you go to a synchrotron, a user facility, where X-ray light or soft UV light is available at 20 eV or so that you can kick out electrons easily from the solid. And then you use these hemispherical analyzers as detectors, where electrons are guided into these detectors. They are basically two hemispherical metals kept at constant potential. And as the electrons go in here, they are actually spread based on their energy in one direction. And depending on at what angle they enter in this detector, you get one component of their momentum in the other direction. So here's the typical data, for example, where what you're looking at here is the energy is obtained from here, and the kx, let's say, is obtained from this direction here. What you are really looking at is this is the surface states of topological insulator. This is the Dirac cone we are looking at here. You can see the bulk states a bit right here. This is the Fermi level. Everything below is occupied. Everything above is empty. Now, one challenge with this experiment is that you only get one direction of the momentum per sample orientation. But we are talking about a two-dimensional brilliant zone. If you want to get the other component of the momentum, what you do is you actually rotate your sample, take another spectra, rotate again, take another spectra. That's how you map the 2D brilliant zone, right? If you also want to know about the spin of these electrons, for example, I told you that these bands are actually spin polarized, right? We discussed that if this is spin up, this is spin down. If you also want to know about this, then it actually gets even more challenging. What you do is you actually punch a hole into this detector, and then you select electrons with a certain energy and a certain momentum, and you let these electrons go through that hole, and you have them be incident on a moth detector, like a gold target. And when they hit the gold, because of the spin or dependent scattering in gold, as the spin orbit coupling is big, the electrons preferentially scatter to the right or to the left depending on their spin state. So that's how you can tell their spin. But this only works for a given energy and a given momentum, like you get this point. If you want to get another point, then you have to rotate your sample and repeat the same thing again. Now, this was very difficult for me to do, because what I want to do is not just take a static ARPES spectra, but I really want to make a movie, right? Because I am interested in understanding dynamics. I'm interested in how, if I excite the system, how does it evolve, right? So for me, it's not enough just to make one frame. I really need to make a movie, a time-dependent movie. So this would be very different with this detector, because I would need to rotate my sample every time. That's why we don't do this at MIT. Instead, we use a different detector. We use a detector based on time of flight spectrometer. So conceptually, it's actually quite simple. Our light source is a tabletop laser, initially at 1.5 eV. Of course, this is not enough. This is below the work function, so we cannot really photoemit electrons. So what we do is we do a high harmonic generation. We go to fourth harmonic. So we have some nonlinear crystals here. 1.5 eV goes in, 6 eV comes out. And then we use these pulses, and then we shine it onto our sample, and then we kick out electrons. Our detector is about a meter-long tube, and from the time it takes for these electrons, we get their energy, because this is a pulse, we know exactly when they come out, we just measure the time, we get their energy, and from where they hit, from X and Y positions, we get both Kx and Ky. So here's how this thing looks in the lab. This is the time of flight analyzer right here. Our sample sits inside this vacuum chamber. Everything needs to be in ultra-high vacuum because electrons cannot travel in air. So the laser is back in here. We have a bunch of optics hidden here and beside this beam block. The laser light is coming through. I don't even know the path. And then it goes into the chamber, and then electrons fly out. And let me show you some data. So after you record this, and this is what you see. So here is the energy, here is Kx, here is Ky. You get this in one orientation of the sample. You don't really need to do any rotation whatsoever. You are directly seeing the entire Dirac cone. And what you see inside, there is this parabolic band here. This is actually coming from the bulk state. So this is Fermi level right here. There are states above this, but they are unoccupied. And everything below is occupied. So this was really great, because now you can do three-dimensional band mapping without rotating your sample. But it turns out that you could do even more. And one thing that we were really interested about was, could we learn anything about the spin texture, right? After all, these bands are spin polarized, and our idea was that if this was taken with linearly polarized light. Perhaps if we use circularly polarized light with different helicity, because these are spin polarized, we might learn something about the spin texture. So we did this experiment in which we recorded the same exact pattern with right circularly polarized light and then left circularly polarized light and took the difference. So here is what the difference looks like. So the light is coming like this. We change, first we take a pattern with right circularly polarized light and then left circular and then take the difference. So what you're seeing here is so white means 0, red is, let's say, negative, blue is positive. And, the bulk states which are spin degenerate don't give rise to any difference between left and right. You can see here, you have negative here, you have negative as well. This is consistent with spin down and spin down here. Here you have spin up and spin up there. So clearly, at least in the qualitative level, you are seeing something related to the spin texture. And then, thanks to my colleague at MIT, Liang Fu, he actually came up with a very simple theory based on just simple symmetry arguments, where you can actually convert this to something related to the spin texture. So it turns out that every one of these points, you can actually infer what must be the spin direction of the electron. So if you project it into plane, you can see that all the spins are actually winding around. In fact, you can even see some higher order features. You can see there's some white intensity there, there's some red here, there's some blue there. This is corresponding to the fact that if you cut this dispersion, it's not entirely a circle. There's some kinks in here. There's like hexagonal distortion right there. It turns out that spins are responding to this, and they are canting out and into the plane like this. This was a predicted theoretical effect, but this is kind of one of the first observations of this. Now, let me stress out one thing. Even though qualitatively spin texture exactly showing what they should be, this is still not replacing the Mott detector for the following reason. To get the overall spin polarization, we would need to rely on the Mott detectors. There's an overall constant multiplying the spin. And that constant could even be negative. We don't really actually know if the spins are going this way or going that way. And it turned out that we were lucky at this energy. We got the right polarization. But even then, that's why I use the term spin texture. We can at least get the texture. We don't know about the magnitude. All right, so this was nice, and after we saw that we actually can shine light and we can, depopulate this right side of the Dirac cone as opposed to left side of the Dirac cone with circular polarized light, then it occurred to us that this actually should lead to something quite important. If you depopulate this side more than that side, actually you should see a current, because now you have a net population that's on this side. In fact, this effect was predicted that you actually should have some photocurrent in a TI. So what we did, David Shea, who was my postdoc, and James McIver did this experiment in which we fabricated some small devices of TIs, and we did exactly this experiment, and we looked for a current. So the experiment looked like this. Light is coming like this, and you do this kind of different excitation of different size, and then you look for a current that is only there when the light is there, that goes perpendicular to the incidence plane. And that current should reverse direction if you reverse right to left. And in fact, we did see that different helicities give rise to currents going in the different signs. So this was another observation of a key effect in the TI. Okay. Now that I have kind of showed you the power of the technique, let's actually now make use of the fact that when we do this experiment, we are doing it with pulses. That means we actually can add time resolution into this. So let's try. So here is the experiment again. We are doing this three-dimensional band mapping. What I want to do now, I want to split part of this laser pulse, and I want to use it to excite the sample. Okay? So part of this laser pulse is going to come in. It will kick the electrons, heat them up, let's say. And then I will come with this other guy and I will take snapshots. But the beauty is that these are exactly synchronized, and I can control when does the probing pulse arise with respect to the pumping pulse. I can either make this arrive before the pump pulse, in which I will just see the equilibrium state, or I will make this arrive certain time after, in which I will see kind of snapshots of how this dispersion is looking at different times. So let's do that. So I will show you a movie. In this movie, what we are going to look at is the difference movie, which means that I'm going to subtract out the equilibrium state to emphasize you the changes made by the laser. Now in this experiment, just like I showed, the pumping pulse is has energy of 1.5 eV, exactly the same as the initial laser. So the band gap in the bulk of this material is 0.3 eV. So the pulse has enough energy to actually make these optical transitions. So what do we expect? Well, what I expect is that as I shine this 1.5 eV light, I will just populate these states, I will depopulate these states, and we should see population of these and relaxation back down. So this pattern is taken 4.25 picosecond before the pump light arrives. You see nothing because I subtracted the equilibrium spectra, so there's nothing in there. Let's run the movie. So after the light hits, you see that these states are populated and these are depopulated. Blue is negative, red is positive. And then as the time goes on, you actually see the relaxation back down. So for example, this thing would be like a broadened Fermi distribution, indicating that the temperature is higher, right? So this is quite nice in the following sense. So the zeroth order thing here is that ARPES is a probe of occupied states. So normally, you cannot see the unoccupied states because they are empty. But now I can occupy them with light, and then I can probe them. But on top of that, if I take cuts from this movie now, it's not the difference movie, the full movie now. You see, this is before the light comes in. You have a nice Fermi edge here. And after the light hits, you see that now these bands are visible. They are populated. This is the bulk states. What is inside is the bulk state. What's outside is the surface states. You could actually analyze them differently. You can just look at the bulk states or just look at the surface states, and you can fit them to a Fermi-Dirac distribution. And you can get chemical potential and the temperature for both separately, right? What we learned from this experiment, for example, that temperatures don't come into equilibrium immediately, right after the pulse, even though they are exactly, on top of each other, bulk and surface electrons, somehow it takes some time, like 10 picoseconds or so, for them to actually come into equilibrium, which is a long time. It turned out that they cannot directly couple to each other. They cannot scatter from bulk to surface because of kinematics. You cannot conserve energy and momentum. They have different dispersion. But they actually talk via phonons. The way we figured this out is we did this experiment at room temperature and at low temperature. They came into equilibrium quite quickly at room temperature because there are a lot of phonons around. But at low temperature, it takes quite a bit of while. Okay, so I don't want to go into details of this because it's kind of old. I want to tell you this our newest experiments in which we asked the following question. What if now we turn the energy of this laser that we are using to excite this thing below the bulk band gap? In other words, now this 1.5 eV excitation was big, so you can do these transitions. But what if you come with a laser that has this much energy, right? Then these are Pauli blocked. You can't really do any excitation. So what should happen? Well, in principle, nothing should happen because the laser doesn't have enough energy to do any excitation. But it turns out that something very, very interesting happens, and that's what I want to show you. So what happens if you shine light that doesn't have enough excitation energy? So what should happen? So after all, light is periodic electric and magnetic fields. What the electrons will do, they will feel a periodic potential. They will feel a periodic potential that's periodic in time. So what does the electrons do when they feel a periodic potential? Well, this is what we do as solid-state physicists all the time. Electrons in a solid are in a periodic potential, but that potential is periodic in space, right? So what happens? This is free electrons, E is equal to 1/2 mv squared, whatever. If you put them in solid with this periodic potential, the dispersion gets replicated, right? With this periodicity of 2 pi over the spacing of between these atoms. Now, if you crank up the interaction between electrons and the underlying lattice, what happens is you open up band gaps at these crossing points. So these are the block bands, and we know these band gaps at the zone edges. Okay, this was actually, I could also express this in the following manner. I have a Hamiltonian that's periodic in space. If you solve this thing, you actually get block states, if you remember your solid state physics course. And, in this block states, k and k plus an integer times the reciprocal wave vector are the same state. So you actually make it such that the wave functions repeat in momentum. Okay, this was the PhD thesis of Bloch. All right, he worked with Heisenberg, and what was his PhD thesis was and ended up being the basic of the solid state. Now the same thing can be described in time. If you have a Hamiltonian that's periodic in time, I could analyze it the same way. Now this time, these states are actually known as the Floquet states. Floquet was a French mathematician that worked on periodic differential equations. And instead of periodicity in momentum, well, space and momentum are conjugate variables, and time and energy are conjugate variables. So you would actually get a periodicity in energy, right? Just like these states repeat in momentum, these states you expect to repeat in energy. If you have both, then this is called Floquet-Bloch states, right? So then you would have both repetition in momentum and energy. Now, Floquet states are very common, at least commonly used as a term in atomic state physics, where you can have two levels. You can shine an RF field that's less than the transition energy. You can dress them. But I was told my atomic physics colleagues that even in atomic physics, their observation is kind of tricky. Now, in solids, before this work, there was no observation of Floquet states whatsoever, because if you shine light into a solid, usually you make direct excitations, and that leads to scattering. You immediately lose this coherence. So what we did is we kind of tried to get around this, and we did the following experiment. Now, in order to see this, I don't want direct absorption, so I need to lower the energy of this light below the band gap. So we put a nonlinear element there called OPA, optical parametric amplifier, which is a standard optical element where we take 1.5 eV in, and then this produces tunable light energy between 80 and 300 MeV. So we selected something like 150 milli-electron volt as our pump. Now let me show you a movie in terms of what happens when you shine light into the sample with energy that's below the band gap, about 150 milli-electron volts. So this is the original Dirac cone, and this movie that I will show you is not the difference movie, it's the full movie. So what we are going to watch is what happens, what changes in this dispersion as the light comes in. So this particular one is taken 500 femtosecond before the light hits the sample, and let's see what happens. So as the light gets in there, I don't know if you can see, but there is maybe we should turn off the lights, but maybe that's okay. Let me run this movie one more time, and let's actually stop the movie at the peak of the light, because this is a pulse. It actually goes through the thing. Here is one more time. So you see, this is the original cone. As the light gets in, you see the replicas here. And let me stop at 0 femtosecond when these two pulses are overlapping. You can see this is the original Dirac cone. This is the first order replica. This is the -1 order. You can even see the second order. Now, lights were a bit bad, so let me actually take cuts. So let me take a cut like this. So if I cut like that, you can see, this was the original Dirac cone, and at 0 femtosecond, when these two light pulses overlap, there is another one inside, right? Let me take a cut with the vertical direction. Let me run the movie right here. So this is the original Dirac cone dispersion of the TI, and after I shine the light, you can see formation of these states, right? And as the light goes out, they actually go out. So let me actually show you the cuts from this movie. So this is before the light hits. Okay, here is the Fermi level. And at the peak of the light, you can see very clearly that besides this original cone, there is the first order, there is the second order, there is the -1 here. You can even see higher order ones. And when the light leaves the system, they're gone. Okay? And if you're careful, you actually take a look, and then because this light is actually lower energy, you're not doing that much heating, at least when the light is there. After they go out, it does heat. Heating is actually determined by how sharp this thing is. Now, if you look at these spacing, that spacing turns out to be h bar omega. So that's great. So this actually means that these are really hybrid photon-electron states. What's really happening is electrons and photons are constantly exchanging, and then these states are not just electrons or not just photons, they are both. They're hybrid states. Okay, so it turns out that this is actually much richer. Okay, in what sense? So let's think about the geometry of the experiment. The geometry is such that we are shining light with an incidence angle of about 45 degrees. And it's p-polarized, meaning that the electric field is oscillating like this. Okay? So in terms of the sample plane right here, sample surface, I can define two directions. One is along the in-plane electric field. I call it kx. The other direction I'm going to define is perpendicular to the electric field. I'm going to call that ky. Now, because I have this time of flight detector that has the entire dispersion, I can cut my dispersion either along kx or along ky. And these are these two cuts. So this is a cut along kx. This is a cut along ky. Now, one thing that you notice, there's some asymmetry in intensity. We understand that that's kind of a trivial effect that comes because our light is coming at an incidence angle, and that is actually related to the spin texture. But forget about that. That's not important. Now, the other thing that's actually much more important is, if you look at this guy, you can see when this order is crossing the original band, there's a gap right here. Same gap you can see over here, or you can maybe take a look. These are a bit curved, right? They are curved rather than being across. Whereas there is no sign of that here. So to convince you, let me take cuts here. So let me take a vertical cut right there. So what you are looking at here, this is before the light comes in, a cut through this space, and after, at the peak of the light, you see this is split, as opposed to right here, which is not split. So somehow, when these bands cross each other along certain directions, you open up gaps. Now, what does this remind you? This is basically what, you are getting this anti-crossing gap, which is identical to this different block orders crossing, right, in the periodic, in space case, right? This is what happens in the block bands. When they cross, you open up gaps. This is exactly the time analog of that. Now, I can test my argument by changing the polarization. Instead of p polarized, I can put s polarized, which is polarization like this. Electric field is parallel to the sample space plane. In that case, then if what I said is true, gaps should appear perpendicular to the electric field. And indeed, look, there are gaps here, right? You can see by eye, but not there, right? So this actually indeed makes sense. So the question is, I didn't really explain why is it that the gaps only appear in one direction but not the other direction. I'm not going to take too much of your time, but I just want to give you a gist of the theory. So there was a lot of theory work done on the Floquet systems before our experiment, and mostly people were thinking about graphene. They were wondering, how can you open a band gap in graphene? And that one possibility was using the Floquet means. And we also actually did a collaboration with Victor Galiski in University of Maryland to simulate our experiment in TIs. And so if I want to give you a gist of this theory, it's this way. So Hamiltonian for a topological insulator can be written like this. If you want, you can relate to this as like k cross sigma. Momentum is perpendicular to the spin, right? This is the Fermi velocity right here. If you want to put light in there, you can substitute you can do a usual substitution to treat the light. This is the vector potential of the light right here. And when you plug this in here, what you get out is, besides the original Hamiltonian, you get this external Hamiltonian. These are the components of the vector potential. For this simple model, we are assuming that this is a step function. You just turn on the light and it stays there. And this V is, a bunch of parameters. This is electrical charge, Fermi velocity. E0 is the strength of the electric field. And omega is the frequency of the light. Now, if you solve this model, this is what you get. Plug in linearly polarized light, which is and has vector potential of this form. And if you do this solution, I'm just plotting energy versus kx, let's say. This is the original Dirac cone. It's linear. When you put the light in there, you see these replicas. This is the first order. This is the -1 order. And in the x direction, they are crossing. Whereas in the y direction, they actually hybridize and you open up a gap. So why is that? Because if you plug this in here, this Hamiltonian commutes with the original one in the x direction, but not in the y direction. So because it doesn't commute in the y direction, you can open up a gap. So in this very simple model, you can actually calculate what the gap is. The gap is simply just V. And that has everything we know here. We know the electrical charge, we know the Fermi velocity. We can put a power meter and measure what the electric field is. We know the frequency. And if you look at the experiment, this particular experiment, we saw about 70 MeV gap. Excuse me. If you calculate this gap, you get something very, very comparable. So this is amazing that they actually agree. Okay, so another check I can do is this gap scales with the electric field, not with the fluence of the light, which is square of the electric field. So I can check if this is really the case. Indeed, the gap is proportional to square root of the power of the light, which means linear in electric field. So that also makes sense. So the last thing that I want to tell you is the following. It's great that we can see these states, okay, that we can put the light in there and we can make these hybrid states of electron and light. And then the question is, can we mess up with the topology of the topological insulator? How do you mess up with the topology, or why do you want to do that? So as you remember, I told you that this crossing point is protected by time reversal symmetry. So if you want to open up a gap, you really need to put some kind of magnetic field or magnetic impurities. In fact, it turns out that for many of the applications of TIs, you do need to open up a gap. You need to make these Dirac fermions massive, for example, this monopole experiment that I was telling you about, or not experiment, theory, people imagining that you would coat with a ferromagnetic layer so that you actually gap these states. Or people actually have tried to put magnetic impurities so that they can gap this. But they have some material problems that it's hard to coat with a ferromagnet. If you put magnetic impurities, you mess up other things. Now the question was, could we use light to actually do this? Could we use light to open up a gap at the Dirac point? How? Well, linearly polarized light wouldn't do it. This experiment that I showed you, it was all linearly polarized. It wouldn't do it because it respects time reversal symmetry, right? What do you need? You need circularly polarized light, which actually breaks time reversal symmetry. So first, let's check that in linearly polarized light, you don't do anything to the Dirac point. So here's linearly polarized light. Again, I am taking a cut across the Dirac point this time. Okay? So here is before the light, and the red one is at the peak of the light. You see that around the Dirac point, nothing is happening. So this is the peak of the light. You can see with your eye, you can perhaps see that there are gaps here. These are the anti-crossing gaps we talked about. But the point is there is no gap at the Dirac point. But now let's make the light circularly polarized. Here is circularly polarized. So you can see with your eyes, perhaps, there's a gap right here. And if you take a cut, you can see that it splits. Circularly polarized light indeed does open up a gap at the Dirac point. Now, you can come back and you can use this simple model again. All you have to do is change the vector potential of the light to the circularly polarized one, and you resolve this model. When you solve it again, you actually see that there's another gap that opens up at the Dirac point. And if you calculate that, you can also see right here. And if you compare this to the experiment, it's not bad. We actually can also, at least in the same order of magnitude, can calculate that as well. So let's get a bit more intuition about this gap. Why does it that you also open up a gap at the Dirac point? So you could do that by looking at the small coupling limit. In this case, when this V is much less than h bar omega, you see that this gap at the Dirac point would scale like V squared, as opposed to this other gap, the crossing gap, anti-crossing gap, which was like V. The fact that it goes like V squared already tells you that this must be like a second order process. Indeed, actually, it was pointed out before our experiment, 2 years before our experiment by these authors, by Liang Fu and Eugene Demler, that the reason why you are getting this gap is because it's as if like your initial state, you are first absorbing a photon and then emitting a photon, and this state interacts with this guy, opening up a gap. What they pointed out, there is an equivalent process in which you can first emit a photon and then absorb one, and this would also interact with this one. They look identical, but it turns out there is some phase difference between the two. Okay. Now, what they showed, this is a bit technical, what they showed is that this Hamiltonian is exactly the same Hamiltonian as the Haldane state, okay, pictured in graphene. So what is the Haldane state? Now, Haldane is a theorist, and he had an extremely brilliant idea, which is that if you take the graphene, and if you put magnetic field such that magnetic field would change direction within one unit cell, so that the net flux is 0, okay? So then you would have no net magnetic flux. What he showed is that the phase of the next nearest hoppings, they are actually different because of this alternating magnetic field. And in this system, he showed that you can get a quantum Hall effect without Landau levels. So without no net magnetic flux, you can still get quantum Hall effect. I mean, theoretically it was brilliant, but it's very difficult to realize a magnetic field that actually changes direction in one unit cell. It's impossible, right? But what these authors say, this state that you realize with circularly polarized light is exactly, mathematically speaking, has the same Hamiltonian. So what does that mean? It means, for example, this should also display Hall effect, right? So you can shine circularly polarized light, and you can look for, without any external magnetic field, you can look for Hall effect. And that's what one of the things that we really hope to see. So without boring you too much, let me actually summarize. What I've shown you is the way how we can do three-dimensional band mapping and spin texture mapping. And then I showed you how we can actually use the pulse nature of our light source to make movies of electronic dispersion in three-dimensional movies. And then by tuning the light energy below the bulk band gap, we were able to see these hybrid photon-electron states. And when they cross, they open up these gaps. And even when you change the linear polarization to the circular polarized light, you can actually also open up a gap at the Dirac point. So I want to leave you with the picture of my group, and thank you very much for your attention. And if you want to know what we are doing next, don't hesitate to ask me.
So what are you doing next?
Brilliant question. So what we really want to do next is a great excuse to keep talking longer, right? Isn't it? So we want to take these initial observation of these states, Floquet-Bloch states, and we would like to do something useful with it, okay? What do I mean by doing something useful with it? So number one, for example, I showed you that we can use it to actually break time reversal symmetry and open up gaps, right? It turns out that the gap that we opened up, it was about 40 MeV. You would need about 400 Tesla to open that gap with magnetic field, right? So this is a very good way to actually mimic the magnetic field. You can observe similar effects in magnetic field. But first, we really need to understand how these states, form and how these states decay. We are actually trying to understand how do these states couple to the other electronic states around it. So, for example, we recently realized that when we shine light into the solid, we are not only addressing the initial state in the solid, but also the final states, and we can actually see the interference of the two. So we can actually, see this interference and make it, only the initial state to rest or the final state. So the other thing that we have done is use this magnetic field mimicking nature of the light, if you wish, to actually do something useful on another system. So this is in these materials called transition metal dichalcogenides, in which they have two valleys that are energetically locked to each other, and this degeneracy of the two valley is protected by time reversal symmetry. So people were trying to lift this degeneracy with magnetic field. The trouble is you would need like 10, 20 Tesla to get like milli electron volt kind of shifts, right? So we tried the same thing, if you wish. We did come with light that's less than the band gap. Then you create these Floquet states, and then they repel each other, and you actually get a bigger energy gap. And the way we probe it, we actually measure the absorption, right? So if you measure the absorption equilibrium, when you put in light, the absorption shifts because this energy shifts. And then with this difference looks like this. Now, it turns out that if you put left circularly polarized light, one of the values shift. If you put right circularly polarized light, the other valley shifts. So you kind of get a valley-dependent shift. You kind of mimic the magnetic field properties of this. So let me skip some of this, and let me actually show you something quite exciting. I think this is kind of, maybe I'll end with this. So one of the dreams in this field is the following. Now that you actually have a way of making new electronic bands with light, if you wish, like coherent bands, right? Why should we just rely on chemistry to change the properties of the materials? Like if you are making hybrid bands, with electrons and light, rather than changing the properties of the electrons, just change the properties of the light, right? So could you use this actually maybe to stabilize phases that are normally unstable? What do I mean by this? Some kind of dynamic stabilization. I want to actually just illustrate this with an example from mechanics. Think about a rigid pendulum, okay? A rigid pendulum has this top point which is unstable, right? It's an equilibrium, but an unstable equilibrium, right? We all know that. If you drive this pendulum up and down like this, that state actually becomes a stable equilibrium. This is known as Capissa's pendulum, right? If you actually study this problem, normally in the undriven case, it is this unstable equilibrium. But as a function of the drive, this thing actually turns into a stable equilibrium, and now you can actually see the oscillations around this. So the idea is this. In materials, in correlated systems, for example, we have so many different phases, and that means the potential energy landscape is such that there are so many in local equilibrium, right? Perhaps by shining this light and doing the periodic excitation, you may be able to turn some of these unstable equilibrium to the stable ones, and that could be very interesting. So that was a long answer to your question.
Are there any more questions before we get to it?
Yeah, the question was, when you're doing these excitations with EV light and looking at how the system thermalizes, can it always be described by an equilibrium?
Very good question. After 200 femtosecond, yes. But right after the excitation, it cannot be, right? Because we put a 1.5 eV, the first thing that we see is that there's something at 1.5 eV. So first it mimics the density of states up until the photon energy. But then quickly, electron scattering is fast, like 10 femtosecond. Within 100 femtosecond, it fits beautifully to the Fermi Dirac. But of course, the temperature goes up to 1,000 Kelvin. This is the electronic temperature, yeah.
I wanted to ask you about this experiment in which surface states did not thermalize for a long time with
Sure.
bulk state.
Yes.
You said it's because they speak to each other through phonons.
That's what we think, yes.
But why do each of them thermalize sooner?
Each of them itself thermalizes immediately. I'm just saying that why? Because of the electronic, they can actually, they can just
speak to each other.
Yeah, you can actually, yes. Well, within each band, you can actually go down thermal. Like people, we did this experiment also for graphene, for example. Not ARPES, but in graphene, it has the identical dispersion. And same thing, you put light, and within 100 femtosecond, the system, the electrons thermalizes. So in a topological insulator, what happens as well, the surface states themselves thermalizes within, and then the bulk states thermalize, but they can't really talk to each other. Because the scattering from surface to bulk involves phonons that are, you can't really match energy and momentum.
And how does surface to surface scattering?
It's still with phonons, but different phonons are involved, right? So you can really go very, very small amount, right, in energy. It is still phonons, but different kinds of phonons.
I'm
yes.
confused.
Yes, sure, yes, sure.
What happens to plasmons when you do this?
That's actually a very good question. We were wondering about that too. So for example, we were wondering when we put the light in there, could we maybe derive the plasmon, etc. In fact, it was such a point that we asked another spectroscopist to measure if actually there was a plasmon in there. Now, one difficulty is it's very hard to excite the plasmons with light because the dispersion doesn't match, right? So if you really want to excite the surface plasmons, you really have to put a feature in there. Yeah. But it would be a nice experiment. If we could excite the plasmons, I would assume that they would also come back and dress our electronic states. Yeah.
Just in your slides from the movie showing the population after the laser pulse.
Right.
So at long times I saw that. So you have population imbalance around the Fermi level,
right.
which I expect, but also you still have a large population imbalance at the Dirac.
Below, yes, that's right. So, right. So what happens is, immediately after the light, you have some population above the Fermi level and some depopulation below, if you wish. And the thing that I call thermalization, basically the holes move up and electrons move down, and then yes, right, exactly. You can, but within 100 femtosecond though, everything looks as if you can define a temperature right around the Fermi level. Right?
I mean, just from maybe if you go back to the pictures, just around the
Dirac cone, yes.
It seemed like there was still a large population.
Are you talking about excitation with 1.5 eV or the Floquet one? Right. I think some of this is, at least below the Dirac point, our intensity is a bit low, and when I take the difference, some noise gets in there. Yeah, so I think some of it is noise.
One more question. Can you measure DC conductivity while you're applying these?
That's a very good question. Yeah, so the question is, when we do circular polarized light, can we measure the Hall effect? We thought about that. We tried briefly. The difficulty is the Hall effect should only be there in 100 femtosecond when the light is going to shoot down, right? So you should get a current that should, but there's another way you could try, which is that if you have a sigma xy, right, the off-diagonal conductivity, if you were to put like terahertz electric field, optical pulse, right, that should actually rotate because now you get that's what we are trying. And that we could do within the pulse because we can actually synchronize the pulse.
So you could look and see if the quantum Hall effect is modified.
For example.
Or you've already opened a gap, you might expect to drive the system into an insulating.
Right, exactly. So doing the spectroscopy of these states is also something that's very novel that hasn't been done.
So maybe we should move the discussion up to the upstairs reception area, and let's thank you.
Thank you.